You may have heard of the big 5 mass extinctions in Earth's history, or that we're currently in the 6th mass extinction. But there have actually been way more than 5 or 6 mass extinctions in Earth's history. And today, I'm going to be talking about all the mass extinctions in Earth's history that nobody really ever talks about. Before we get into the lesser known mass extinctions, let me talk a little bit about the big 5 mass extinctions that pretty much everybody talks about. These include the End-Ordovician mass extinction, which occurred around 444 million years ago, which I have a video on and I'll link it up to the top right for you. Then the late Devonian mass extinction hit around 365 million years ago. I will also link my video on that one to the top right for you. Then we had the End-Permian mass extinction, nicknamed the Great Dying, around 250 million years ago, because that was the largest mass extinction of all time, and I will link that one to the top right for you. And then we had the End-Triassic mass extinction around 200 million years ago, just following that one. And finally, we had the End-Cretaceous mass extinction around 65 million years ago. And I have individual videos about all of these events, and I will link as many as I can to the top right, but there's a limit, so I'll just link the rest in the description box below. Now, these, like I mentioned, are the big 5 mass extinctions, meaning that they're basically recognized as the top 5 or greatest 5 mass extinctions throughout Earth's history. But there have been many other mass extinctions that rival the magnitude of these top 5 mass extinctions, and today I'm going to be talking about several of them, which are now listed on the screen. So if we take out the big 5 mass extinctions here, we can see there was a Precambrian one, Cambrian extinction, Silurian extinctions, late Devonian and End-Devonian extinctions that are separate events from the late Devonian extinction that we recognize as the top 5 mass extinctions. And then we had one in the Carboniferous period, or the Mississippian to Pennsylvanian boundary, then the early Triassic, which is separate from the end Triassic mass extinctions, and the Jurassic period between the Triassic and Cretaceous periods. There have been many others, but these are some of the major ones that are not included in the top 5, but are very high up on the magnitude or severity list that we'll talk about today. Hello, Editing Rachel here. So it turns out that the video with all of these extinction events was really, really long, so I'm cutting it into 2 parts. This first video will cover everything from the Precambrian till the mid to late Devonian, and the second part will include everything from the late and end Devonian extinctions until the Jurassic extinction. So come back next week to see the rest of it. Okay, back to the video. So let's start with the oldest in the Precambrian. The biosphere, or life on Earth, was dominated by anaerobes before the GEO. What does this mean? Well, anaerobes are microbial organisms that don't need oxygen to live. In fact, many anaerobes don't like oxygen at all. It's toxic to them. And the GOE is the Great Oxidation Event, which marks the first appreciable buildup of molecular oxygen, O2, in the oceans and atmosphere, which is what we animals breathe. Many of these anaerobes were obligate anaerobes, which not only don't use oxygen, but can't stand it. It is toxic to them. And because of this, the sudden oxygen increase at the GOE caused the extinction of many of these species. Up to 90% of all species on Earth at the time went extinct, or at least these are estimations based on a very patchy fossil record from the Precambrian time. Now, I want to specify here that the only reason that the Precambrian extinctions are not included in the top 5 mass extinctions, well, one of the reasons is because the fossil record is just really incomplete for the entire Precambrian, because again, this is microbial life. Large animals with hard parts that actually got preserved more often in the rocks had not evolved yet. They came later during the Ediacaran Cambrian boundary around 600 to 500 million years ago, and then evolved from there. But before that, in the Precambrian, anywhere from 3.5-ish billion years ago till 600-ish million years ago, it was all pretty much microbial, and because of this, the fossil record really just sucks. So we can't say a lot about that, and that's why most of the recognized extinction events are after animals with hard parts evolved so that we can actually recognize the extinction events in the rock record. However, because our understanding and our ability to reconstruct geochemical conditions using geochemical proxies in the rock record have greatly advanced over the past couple decades, I do have an entire video about how life went from hating to loving oxygen, or anaerobic to aerobic life, during this Precambrian time, and I will link that video to the top right if I have any more cards available to link. If not, I'll link it down in the description box below and you can check that out. But moving on now to the next mass extinction events within the Cambrian period, which was around 540 to around 485-ish million years ago. So now we're way further in Earth's history in the Cambrian, once we finally had more large organisms, more hard parts, and all of this stuff that allowed us to have a more complete fossil record and see what was actually going on. Numerous extinction events actually occurred within the Cambrian period, even though none of them are included in the big 5 mass extinction events. And this is largely because the intensity of the Cambrian events is hard to discern due to, again, the patchy fossil record. The Cambrian was when we had animals begin to evolve in a better fossil record than the Precambrian, but it was still during this transitionary period in which there was still a lot of soft-bodied organisms and small organisms, and we weren't to the point yet that we had very large and preservable organisms that created a more complete fossil record. 3 or more Cambrian extinctions have been identified to date, and these include the Devonian extinction event, the Drisbachian extinction event, and the Cambrian extinction event. Now, if I'm pronouncing any of these names wrong, please call me out politely in the comments below. I would love to know how to correctly pronounce these. First, we'll start with the Devonian extinctions. This is when early Cambrian archaeocyathids, which were like sort of coral-like, potentially sponge-like organisms that are shown in a reconstruction down to the bottom left. These organisms, as well as small phosphatic shelly fossils called the Timoshan fauna, were replaced by more familiar mid to upper Cambrian fauna. Now, I talk about the 3 distinct sets of fauna that evolved throughout the Cambrian period in my early Paleozoic life video, which I'll link below because I don't think I have any more cards available to link. But anyway, these fauna represented kind of the early Cambrian set of fauna, and then they were replaced after this extinction event by the mid to upper Cambrian or mid to late Cambrian fauna. The apparent extinction of small shelly organisms, however, may be a function of poor preservation of phosphatized fossils at the time. Now, just to give a little background, typically shelly fossils, or organisms that produce shells that get preserved in the rock record, can be either made of calcite or aragonite, which are calcium carbonate minerals, or phosphate minerals like calcium phosphate. And if that is the case, that's a slightly less preservable mineral in certain cases, depending on ocean chemistry. And at the time, the ocean might not have been favorable for phosphatized fossil preservation. And if that is the case, then the fossil record might be what is causing this apparent mass extinction, when in reality it's just lack of preservation, not extinction. Another caveat to this potential extinction event is that archaeocyathids, that coral/sponge-like early organism that potentially went extinct at this extinction event, seem to continue beyond this extinction event boundary and actually disappeared in the Toyonian after the Devonian extinction event. So here in the figure to the left, we can see the timeline of the Cambrian period, as well as carbon isotope records during this period, and the timeline of extinction events throughout this period associated with certain carbon isotope excursions. Stable carbon isotopes, if you don't know, are very promising records of climate change events, specifically global warming events, by way of recording periods of major carbon burial or release. I talk about this in my stable versus radioactive isotope video, as well as my carbon isotope video. I will link those below as well. In any case, the timeline of extinction events over here, we can see that the potential Devonian extinction is placed around 514 million years ago, but this is just before the recorded extinction of the archaeocyathids in the Toyonian, which occurred around 510-ish or 11-ish million years ago. And so because of this discrepancy in timing, it's still not fully clear whether the Devonian extinction was kind of a prolonged event, depending on locality, or if there were two discrete extinction events and the second one took out the archaeocyathids rather than the first. Just after the Toyonian red lichid and olanellid trilobites went extinct, which coincides with a major negative isotope excursion, as shown here on the figure, around 509 million years ago, and it's still not currently clear whether the Devonian, Toyonian, and early Cambrian extinction of those trilobites were one single prolonged event or 2 to 3 distinct events. When combined as one single prolonged event, all of these extinctions add up to a loss of about 70% of all faunal diversity. And the trigger for climate change that potentially caused these extinction events was probably LIP eruptions, or large igneous province eruptions, in northern Australia around 510 million years ago that likely caused major carbon dioxide release and associated warming and ocean anoxia, or a lack of oxygen in the ocean. This caused a major negative carbon isotope excursion around 510 to 509 million years ago, called the ROECE excursion, or the red lichid olanellid extinction carbon isotope excursion. And as we can see, the Devonian extinctions, as well as potentially even the archaeocyatid extinctions in the Toyonian, might have occurred just before the large igneous province eruptions, and therefore the timing doesn't match up to say whether this whole event or the prolonged event was all caused by the lip eruptions, or just the final event that caused the extinction of those trilobite groups, or whether there were lip eruptions that occurred before 510 million years ago that set off those two previous events. There's still a lot of unanswered questions here, but this is potentially one of the major Cambrian mass extinction event or events. The next one we'll talk about in the Cambrian is the Dresbachian extinction, which is more mid to late Cambrian. This event may have added up to about 40% of marine genera loss. Among these losses were numerous trilobite genera, which went extinct around 497 million years ago. And this event coincides with, or occurs just at the onset of, a major positive carbon isotope excursion, actually one of the largest positive isotope excursions in the Phanerozoic eon, called the Spice event, or the Steptonian positive carbon isotope excursion. And it's thought that enhanced coastal upwelling and ocean anoxia increased organic carbon burial, which likely caused the Spice event, or the carbon isotope excursion and extinctions. The reason organic carbon isotope burial causes a positive carbon isotope excursion in carbonate material is because organic carbon preserves very light, isotopically light carbon-12, and that leaves behind more heavy carbon-13 for things like carbonate material to use to make calcium carbonate. And so when organic carbon burial rates greatly increase, that causes a great positive carbon isotope excursion observed in carbonate materials. Again, I talk more about that in the isotope videos. I won't get into it here. In terms of extinctions, the local anoxia, or lack of oxygen within regions of the ocean, likely continued until the end Cambrian. So all the way after the Spice event for, 15-ish million years until the end Cambrian, contributing to extinctions among brachiopods, conodonts, and trilobites. The end Cambrian event, which is marked by this negative carbon isotope excursion around 485 or 486 million years ago, was less severe than the earlier Cambrian extinctions we talked about. However, it was followed by one of the big 5 mass extinctions, the late Ordovician mass extinctions, in the next period called the Ordovician period. However, like I mentioned at the beginning of the video, I do have a video already talking about the late Ordovician mass extinctions, so I won't get into that here. I will, however, talk about the Silurian mass extinctions, because just following the Ordovician period came the Silurian period, and in the Silurian there are some mass extinctions that occurred, or likely occurred, that are not included in the big 5 mass extinctions and are rarely ever talked about. Life rebounded rapidly in the Silurian period right after the late Ordovician mass extinctions, with the appearance of bony fish and small vascular plants. However, minor extinctions, including the Eryvgian Precambrian, Mold, and Lao mass extinctions. Again, I'm sorry if I'm mispronouncing words. Please tell me in the comments how to correctly pronounce these events. The first of these three minor extinction events in the Silurian affected graptolites, which are shown in the picture down below. They are now extinct, but here is the picture of them in the fossil record, as well as a reconstruction of what the graptolite animals would have looked like. Conodonts, which are also shown below and are also fully extinct, but there is a reconstruction of what they would have looked like and their fossils in the rock record, which are mainly just their teeth. And trilobites, which we all know very well, are, our favorite little Paleozoic ancient sea cockroaches. And these guys are also fully extinct now, but were dominant with much diversity in the Paleozoic era. At this time, all of these groups suffered losses, while shallow water reefs were actually barely affected. This event is marked by carbon and oxygen isotope excursions, and the most likely cause was deep ocean anoxia, and so it was only really affecting the deep ocean and not so much the shallow water reef systems, which is probably what kept it relatively minor. The later two events coincide with sea level falls and positive carbon isotope excursions attributed to widespread organic carbon burial and likely cooling that caused the sea level to fall due to increased glaciation. And these events caused extinction among conodonts and graptolites again, but again, these were, very minor compared to pretty much all the extinctions in any other period throughout the Paleozoic era. Next, we have the Devonian extinctions. The Devonian period, which went from around 400 to 360 million years ago, marks probably the most drastic mass extinctions and is just, it was a real rough period for life. The reason for most of the Devonian extinctions is due to repeated transgressive anoxia. Anoxia, like I mentioned earlier, means a lack of oxygen in the ocean, and transgressive means that there was sea level rise at the time. The reason that transgression or sea level rise and anoxia would coincide is mainly due to warming events. During warming events, sea level rises due to ice melting, and anoxia forms due to an increase in CO2 and therefore primary productivity or photosynthesizing blooms at the ocean's surface, which cause aerobic organisms to use up all the oxygen below such blooms, and then in the deep ocean it causes anoxia. Another reason warming causes ocean anoxia is due to a change in ocean circulation. When you have a lower temperature gradient from equator to poles during warming periods, you cause a stagnant ocean, or you decrease ocean circulation because it's driven by thermohaline circulation, which means temperature controlled and salt controlled circulation. And when the temperature isn't changing enough to cause cold waters at the surface that meet the poles to sink, the circulation decreases. And so you have stagnant oceans, which end up causing deep ocean anoxia to spread because you're not getting the surface ocean oxygen to mix with the deep ocean, and the lack of mixing and lack of circulation and using up of oxygen during primary productivity blooms, all of that exacerbates ocean anoxia. There were up to 9 widespread hypoxic to anoxic events during the Devonian. Hypoxic is similar to anoxic, but instead of a complete lack of oxygen or absence of oxygen, it's more depleted oxygen, so very low oxygen, but not fully absent. And so in terms of lowering oxygen, there were up to 9 events that are shown in the graph here to the left throughout the Devonian period, and each is associated with transgression or sea level rise. The first two are associated with ammonoid extinctions, particularly in the goniatite group, which is a group of ammonoids with specific suture patterns within their shells. And this group lost 75% of their species by the end of the second anoxic pulse. The fourth anoxic pulse caused repeated extinctions among the same group, the goniatite ammonoids, as well as conodonts and tentaculatids, which are this peculiar group, kind of like the archaeocyathids from what I could find, in that they didn't belong to any modern phyla that live today, modern major invertebrate groups. Instead, they kind of were like their own thing. They look to me in the fossil record like cephalopods, but apparently they were kind of in their own group, or at least taxonomically currently they are not associated with any known modern phyla. The fifth pulse again caused extinctions among goniatites. Those poor ammonoids were just not doing great at the time, and it also caused extinctions among low latitude to corals and stromatoporoids, which were very important reef builders at the time, both corals and stromatoporoids. Stromatoporoids are also similar to archaeocyathids in that they don't really belong to a modern group, or at least there's still debate regarding whether they belong to corals or sponges, but I think most people put them in one of those two groups. In any case, they are fully extinct today, but at the time in the Devonian, they were major reef builders, as were all corals, as they continue to be today. And so the loss of many of these species was really detrimental to not only the species themselves, but the groups that rely on reef ecosystems. However, the greatest extinction during the Devonian period occurred around 10 million years later. But you will have to wait until next week to hear about that extinction event, as well as the rest of them up until the Jurassic. Hey, at least you don't have to wait 10 million years. So with that, I hope you enjoyed watching. As always, my references are linked down below in the description box. If you want to check out this awesome Team Trilobite hat, you can do so. It is at my website where I sell merch. It is also linked in my description box below. And I hope to see you guys back here next week to finish up our discussion on these lesser known mass extinctions and to finally rank them from top to bottom with the big five. See you there. Bye.